So I can do it like this. Impulse, and then the area under the curve would be 1/2 the base. The base here is 8 milliseconds. So I'm literally just calculating the area of a triangle. 1/2 the base, and then the height is F max. Oh, -3. It's milliseconds, yeah. Good. So we're trying to figure out the maximum force here. So I have to do a little bit of algebra. 2 times the impulse divided by 8 to the -3rd is F max. So we've got 2 and then 6 Newton seconds divided by 8 to the -3rd seconds is F max. 1.5 times 10 to the 3rd, it looks like, maybe. Let's see if that makes any sense. The seconds cancel out, so we're left with newtons. So this would be 2 times 6, which is 12, divided by 8. So I think that's 1.5. And then 10 to the -3rd, when you bring it up to the numerator, becomes 10 to the +3rd. So 1, 2, 3. 1,500 if you want to. You could do it like that. So 1.5 to the -3rd, or newtons, or 1,500 newtons, same thing. Now I bet your answer was off by a factor of 2. Okay. Okay, you're welcome. The average force is half of the maximum force. Okay, good. All right, excellent. Any other ones from that homework? It's been hanging around for a while, right? Because we had fall break, and it goes back for over almost 2 weeks, I think. Yeah, sure. Yeah. Just tell me, we can take a look at it. Is it it's a homework one?
Yeah, number 4 I have 3 left.
Okay, homework 4?
Yeah.
Okay. Do you have any homework 5s while I got it open? Oh, okay. Yeah, let's look back at this 4. Whoops. Oh, yeah, can't see. This one here? Okay, so blocks of 2, 3, and 4 kilograms are lined up in a row. All 3 are pushed forward by a 3 Newton force applied to the 2 Newton block. How much force does the 3 exert on the 4? Okay, let's take a look at it.
If I got that part right, it was the second part. I don't know if that was the first part or the second part.
So let's draw the picture real quick. Oh, yeah. So the first part was how much force does the 3 exert on the 2? Oh, sorry, no, that's the second part. The first was how much does the 3 exert on the 4? So we got the first part by saying there was a normal force from 3 on 4, normal from the ground, and then the weight. So it turned out in this part, this is the only force that's going this way. So it just turns out to be mass 4 times the acceleration to get this one. And then part B, how much force does the 3 exert on the 2? So there's a couple of ways of doing this. We could look at the free body diagram for this one. This was, you might have different numbers. Do you have 13 newtons applied to it?
Yeah.
Okay. And then there's the normal from 3 on 2. Really, that's what they're actually asking, the normal force from 3 on 2. So this is the free body diagram for 2. So as you push 2 this way with 13 newtons, if you just want to think about this mass 2, what keeps it from really accelerating more? Well, it's because there's a normal force between those two. So we could use Newton's second law, mass 2 times A, and then we've got to fill in this part. So 13 newtons to the right minus normal from 3 on 2 back to the left. So I on purpose drew this one bigger than this one. Say that one more time, sorry.
Like the first, it's the Newton's, right? 3 on 2 you have right now.
Oh, it's normal force. Normal force, yeah.
Okay, and then how do you find that?
So,
How the mass is?
so we got the acceleration from the first part, and this is 13 newtons. So I'll have to do a little bit of algebra. I'm going to put this over to the left-hand side. So let me actually do that. So I'm moving this over here, and then subtracting m2a from both sides. And then we have this as just given in the problem. We must have got the acceleration probably in the beginning. It would probably be, let's see, 13 divided by 9, whatever that turns out to be. Do you have the acceleration from the first part?
Would it be?
1.44. So I think we did, in the beginning, we got the acceleration of the whole system here. So once you have the 1.44, we can do 13 newtons minus 2 kilograms times 1.44. So I get like 10.12. Let's see if that works. Yes, good. The 1.44 we got by looking at the whole thing as a system. So I think you had to get this to do part A, and then this will be like part B. All right, cool. Okay. Oops. So this one we have an external force that we're trying to figure out, and there's block A and B, and then a rope between them. And these ropes actually have mass. So the figure shows 1 kilogram blocks. All right, they have the same mass. The entire assembly is accelerated up. So that's nice. In the previous one, they didn't give us the acceleration. Here they actually do. So we want to figure out what is this force, this outside force, F. And then we got all these other parts here. So we just kind of got to work it, from the top down, doing free body diagrams of all these individual masses. So let's take a look at the picture here. So here's this outside force. This one's called A. This one's called B. And there's just another rope hanging out here. So these masses are the same. And then the ropes also have the same mass. 250 grams or 0.25 kilograms. The acceleration of the entire system is 3 meters per second squared. So by the system, I mean like A, the rope, this mass, this rope. They're all together, so they all have the same acceleration. Okay, so we want to know, what is this force F? So if I just looked at the free body diagram of the whole thing, just thinking about it as a unit, I would have this force here, and then the total mass times g down. So this means total mass. That would be this mass plus this mass plus this plus this. So the total mass is 2.5, it looks like. So 1 plus 0.25 plus 1 plus 0.25. So 2.5. So looking at it as a system, this is what I have. Those are the only forces on the system. Okay. So I could use Newton's second law. The net force is the total mass times A. So this would be this random force that you're just calling F minus the weight of the whole thing. So this is the part that I had to supply here. So this is always right. Net force, M times A, and then these are the actual forces. This one and this one. So I'll have to do a little bit of algebra, add this to both sides to get this, this external force here. So 2.5 kilograms times, they gave us that, 3, and then plus 2.5 kilograms times 9.8. I'm running out of room here. So this thing is equal to 2.5 times 12.8. 32, it looks like. Does that work?
Yeah.
Okay, good. It's good to check this one as you go because all the subsequent ones depend on the previous one.
Yeah.
And then what is the tension in the top of rope 1? So let's do the free body diagram of mass A then. So for mass A, these are just the forces on A. This is that force that we just figured out. Here's the weight of A, right, M times G. And then there's also the tension at the top of 1. So these take some practice, like how do I know the tension in top of rope 1? How do I know how to look at the free body diagram for mass A? Well, I know that that's one of the forces on mass A because this is rope 1, this is rope 2. Tension always, in a rope always pulls. So as you try to lift A upward with this outside force of 32 newtons, the weight force is pulling it down, but it's also connected by a rope here, so that's also pulling it down. And then the only thing that you don't know, you know this, you can figure out what this one is. We'll have to use Newton's second law again. So the net force is mass A times A. And then we'll have to put in this part. This is the first time that we've actually had 3 forces in this box. So 32 newtons up minus MA, little mass A, times G minus tension at the top of 1. And then again, the only thing that you don't know is what you're looking for. It just is going to take some work. I mean, we know mass A and we know A. We know, this is just 32. You know this part. The only thing that you don't know is this. So you have to do a little bit of algebra to be able to solve for that. We're getting low on time, so
Yeah.
let me just do the algebra real quick. Top of top tension of 1. I'm putting that over to the left-hand side. 32 newtons minus MA times G minus mass A times A. So I took this, put it to the left-hand side, by subtracting it from both sides. Or sorry, actually adding it to both sides. And then subtracted this from both sides. And so without putting the numbers, that's the way you do it. The tension at the bottom of rope 1. So it's the same idea. Let's do the free body diagram for rope 1. So this is for rope 1. So you got the tension at the top of 1. That's really what's pulling the rope up. You got the weight of the rope, so mass of the rope times G. And then you got the tension at the bottom of 1. And that's what we're trying to figure out, the tension at the bottom of rope 1. Same thing, you'll know this from the previous part. This is just the mass of the rope times G. And then the only thing that you don't know is this. So we can do the same thing. The net force, mass of the rope times A, and then we'll have to put this part together. So what's making it go up is this one. You won't have to subtract mass of the rope times G, and then tension at the bottom of 1. And then the only thing that you don't know is the tension at the bottom of 1. So a little bit of algebra, you'll have to rely on top of tension 1 from the previous part, this part, but you can get that. This is just the weight of it. That's the mass of it times A. Oops. Darn, there we go. And then I'd say for part D, we can, let's do this is the free body diagram for rope 2 to get that part. So we got the top, they're calling it T3 actually, top of rope 2. Okay, so they're calling it T3, so I'm just going to call it T3. And then we, the only other thing that we have for this one, because it's not attached to anything else, is the mass of the rope times G. And then this one's not as bad. Net force, mass of the rope times A, T3 minus mass of the rope times G. So mass of the rope times A plus mass of the rope times G is equal to what they're calling T3. Yeah, that's a long problem. All right, yeah, think about it though, put it together, and the one in the test would not be as hard as this one.
Okay.
So if you can do this one, you're in good shape. All right, very good.